Let us now consider work and power in rotating systems. So we have a circular object, and we're going to rotate it from the center mass, which is right about here, at some angular velocity. Radius r, we're going to apply a tangential force. So the force is applied to the edge, and it's perpendicular to r, since it's tangential, of course. And as this rotates, doesn't really matter what its angular velocity is, nor its angular acceleration. But as it passes through a distance, as we realize work is in general a dot product, so as it passes through distance ds, then it has gone through d theta as well. So the force is continuing to be tangential to the object. So work, the differential work done in passing through d theta and moving ds is f tangential ds, which of course ds is r d theta, so it's f tangential r d theta. And you know what f tangential r is, since they are perpendicular to each other. R cross f, that is torque. Now dw equals torque d theta. So the work done in the entire motion that is under consideration from theta 1 to theta 2 is the integral of torque d theta. And of course then torque can be a varying quantity. It can vary with respect to theta, or t for that matter. So this can be a varying torque. Now if torque is constant, which it would be if the force tangential is constant here, it's just the torque times the difference in the angle. Now what about power? Well, power is rate at which work is done. So that's torque d theta dt. If you look at this integral, if we differentiate this, dw is torque d theta. And then divide both sides by dt. So we have rate of change of work is torque times angular velocity, or the rate at which the angle is changing. So there we go. Power is torque omega. Now this is analogous to what we knew from translational considerations. Power is force times velocity. So there is another fundamental rotational relationship in our arsenal. Let's just consider a simple problem with power here. And I'll use it as an example, my Ram truck. So there it is. Isn't it a beauty? All right, well anyway, we're going to assume for the moment that it's producing 400 horsepower, which it does with ease these days, especially after the last round of injectors and twin turbos that I have equipped it with. It's more like probably close to 600 horsepower. In any case, 400 horsepower times 746 watts per horsepower gives us over 250,000 watts, almost 300,000 watts, fundamental unit. Omega 2200 revolutions per minute. Let's convert that to radians per second. So 2 pi radians per revolution, and then convert that to seconds. We get 230 radians per second. So there's omega. And as we just learned, power is equal to torque times omega. So torque is power over omega. So let's just plug the values in, the fundamentals. 298,000 watts over 230 radians per second, 1,300 newton meters. Granted, you probably have little context for that torque. Foot-pounds would be something you could probably have a better intuition for. And let's go ahead and convert that then. 1,300 newton meters. And let's divide it by 4.45 newtons per pound. And then let's convert that to feet. Getting rid of the meters, 3.28 feet per meters gives us, well, the truck is able to produce well over 1,000 foot-pounds of torque in its current condition, which is really, you could say, the twisting force at the rear wheels that not ultimately, but is responsible for the acceleration of the 7,000-pound truck. Under gravity's influence, namely on the surface of the Earth, and so that results in a significant acceleration for this fairly massive truck.